A function can be thought of as taking numbers in its domain and mapping them to numbers in its range. For example, consider the actions of this function. It takes -3 and maps it to -2. It takes 0 and maps it to 1. It takes 3 and maps it to 4. It takes 4.5 and maps it to 5.5. This function has been taking any number we give it in the domain and mapping it to one more than that number in the range. Using the notation that numbers in the range are thought of as y values, we could write the rule for this function as y equals x plus 1. But a better way to express the idea of the function as a mapping is to use function notation. F maps R into R, where f of x, in this case, is equal to x plus 1. The set we write in this position is the domain. That is, the collection of numbers from which we are allowed to select our x values. And the set that we write in this position is something called the codomain. The codomain is a set that has to incorporate the range. So the range has to be inside that set. And then we have the rule. This rule is telling us that f acts on x to produce x plus 1. We have an analogous situation with transformations. It is sometimes useful to think of a transformation as a mapping. A transformation maps a point in a plane to its image, which is another point. Consider the transformation that maps 0, 0 to its image, -2, 1. And 3, 4 to its image, 1, 5. And 0, -3 to its image, -2, -2. Have you worked out what this transformation is doing? It's taking points in the domain and translating them 2 units to the left and 1 unit up. So xy is mapped to x minus 2, y plus 1. Using the notation that image points are labelled x prime, y prime, the rule for this transformation could be written as x prime, y prime equals x take 2, y plus 1. Or we could split this into 2 rules. X prime is equal to x minus 2 and y prime is equal to y plus 1. That is, we're saying that the image x's are equal to the original x's minus 2 and the image y's are equal to the original y's plus 1. This system of equations can also be neatly written in matrix form as x prime, y prime is equal to the sum of these two matrices, xy added to -2, 1. Now we can also express our transformation as a mapping. T maps r squared into r squared, where t of xy gives us this image. Just like the set R refers to numbers on the real number line, here the set R squared refers to points in a plane, where each point is made up of two real numbers. So here we have a point maps to a point. Now the rule tells us that the transformation acts on the point xy to produce this image, or, if you like, rewriting the image to produce this point, x minus 2, y plus 1. Looking closely at the structure of this matrix equation, we see that the image point is represented by this matrix, the original point is represented by this matrix, and the information about the translations is contained in this matrix. Any number in this position is added to the x value, and so it represents a horizontal translation. If I change this to a positive 1, then that would be a translation of 1 unit to the right. If I change it to a negative 4, then it would be a translation of 4 units to the left. Similarly, any number in this position is added to the y value, and so it represents a vertical translation. If I now change that number to a 7, then this will be a translation up or in the positive y direction of 7 units. If I change that number to a negative root 2, then it will be a translation of root 2 in the negative y direction, or root 2 units down. Here are a few examples of familiar functions and their images following various reflections and dilations. We've seen how to represent translations with a matrix equation, but what about transformations like these? Reflections and dilations involve multiplying the x or y values by a number. So a matrix that is multiplied to the original point matrix is required. It turns out that the information for these and many other transformations can be contained in a 2 by 2 matrix. Let's start by looking at the effect of reflection in the x-axis on a single point. A point xy that is reflected in the x-axis becomes the point x minus y. The x value stays the same, or we can think of it as being multiplied by 1. However, the y value is multiplied by minus 1. So the question is, what sort of matrix multiplied to our original point matrix gives us the image x minus y? Now, placing 1, 0 in the first row of our matrix, we need to remember how to multiply matrices. This row is taken into the second matrix, and the numbers that line up here are multiplied, and then the results are added. So we have 1 times x and 0 times y. Added together gives us x, which is the first entry that we have here in our image matrix. If we now place 0 minus 1 in the second row of the matrix, and we multiply as we did before to, to our original point matrix, we find that the 0 lines up with the x and the -1 with the y. So we multiply once again the numbers that line up. And then we add, and we have the result -y, which is our entry in this part of our image matrix. So now we have the transformation matrix that gives us reflection in the x-axis. When it comes to reflection in the y-axis, the point xy is mapped to -xy. This time the x value is multiplied by -1 and the y value stays the same or is multiplied by 1. If we put -1, 0 in the first row of the matrix and we multiply to the second matrix, we get -1 times x plus 0 times y, which does give us -x, the first entry in the image matrix. And if we now place 0, 1 in the second row of our matrix and we multiply once again, we have 0 times x plus 1 times y, which gives us our second entry here. And so we have the transformation matrix required for reflection in the y-axis. Reflection in the line y equals x results in the point xy being mapped to the point yx. Can you think of the entries in this transformation matrix that will have the desired effect? Any number in this position is multiplied to x and any number in this position is multiplied to y. So in this case, 0 x's plus 1 y will give us y as the first entry in our image matrix. Similarly, any number that we place here is multiplied to x and any number that we place here is multiplied to y. So this time 1, 0 gives us 1x plus 0 y's and a result of x in this position in our image matrix. And so now we have the transformation matrix that will give us reflection in the line y equals x. Given that a is some sort of positive real number, dilation from the x-axis by a factor of a results in the point xy being mapped to xay. The y value has been multiplied by a, and the x value is unchanged or multiplied by 1. On the other hand, dilation from the y-axis by a factor of a results in xy being mapped to axy. This time the x value is multiplied by a and the y value is multiplied by 1. Pause the video now and see if you can write down the transformation matrices for these two types of dilation. To achieve this entry in the image matrix, we need 1 times x and 0 times y. So 1 and 0 are the required entries in the first row of the transformation matrix. And to achieve the second entry in the image matrix, we need 0 times x and a times y. So 0 and a are the required entries in the second row. To achieve this entry in the image matrix, we need a times x and 0 times y, so a and 0 are the required entries in the first row of the transformation matrix. And to achieve the second entry in the image matrix, we need 0 times x and 1 times y, so 0 and 1 are the required entries in the second row. How did you go with these questions? I hope this video has helped you to clarify the basic notation and ideas around using matrices to show the effect of a few familiar transformations. In the remainder of this series, we'll take a look at how to show several transformations in a single matrix equation and how to make use of such equations.